Morning, ladies and gentlemen. Welcome to the video notes for chapter 8, section 7, which is entitled Vectors. Vectors are a new idea to most geometry students. You've probably never heard of vectors before. They're going to be infinitely important in advanced science and mathematics. So, we first need to define the word vector. A vector is a number, but it's not just a number. It is a number that has both a magnitude, a value, and a direction. When we look at notation, it looks like a ray, but we no longer use the vector. Okay, we say vector AB. Okay, so this symbol here means vector. We always list the starting point first and the ending point second, just like when we name a ray. Okay, so the magnitude of AB is known as R. Can also be known as the, alternatively can be written as the absolute value of the vector. Is another notation for magnitude that you may see somewhere down the road, say in physics. If we're talking about this vector AB, then point A is known as the initial point or starting point of the vector, and point B is known as the terminal point of the vector. Now, when we talk about direction, basically what we do is we make a right triangle out of vector AB. So this would be a 90-degree angle here. And this angle here between what would be a positive x-axis and the ray is known as the direction, theta. Okay, now we'll get into direction in a lot more detail because that does depend on its actual values, but it is the angle between a vector and the positive x-axis. And again, that would require us to be in standard position. So we've got a lot more to talk about when it comes to direction. Just know that every single vector has a magnitude and direction, which gives us one of the two ways that we can write a vector. We would write it magnitude at direction, or R at theta. Okay? Again, that says magnitude at direction. So it tells us how long the ray is and what direction the ray goes in. We've got to talk about direction in a lot more detail. So, moving on to standard position. A vector is said to be in standard position if its initial point is located at the origin. Okay, if we start at 0, 0, then we will have our vector in standard position, and if the vector is in standard position, then we are able to write the vector in its other form, which is known as the component form, okay, which would be an x component and a y component, a horizontal component and a vertical component. Now, the terminal point would be located at xy. So when we write that in vector form, the triangular brackets here are indicating that it is a vector. Okay, these mean vector. Okay, so vector CD, we're going to write vector CD in standard position. Now in your notes, The blue vector should not be there right now, so let's get rid of that. You should only see the red vector on your own blank notes. And that vector is CD. So C is at negative 3, 4. That's this point here is point C. And point D is at 2, negative 3. This is point D. So you'll see again that we've got that vector very clearly indicated as pointing from C to D. Okay, so we're going to take that vector, we're going to redraw it in standard position. So you'll notice that from C to D, we need to go down and right. So you'll notice we go down 1, 2, 3, 4, 5, 6, 7, and right 1, 2, 3, 4, 5. So what we're going to do is we're going to move C to the origin. So that would be the image of C, or C prime. Okay? And if we move C to there, then our vector, which is this red ray here, if we copy and paste that vector, and then we move it, uh-oh, that shouldn't have done that. What did it do that for? Okay, so CD, let's fix that real quick, goes from there to there, okay? If we move C to the origin, then D would now be located at 5, negative 7. So it would be right here. Okay, and we would have our image of D, D prime, would be located here at the point 5, negative 7. As such, we can state that vector CD has the coordinate or component form 4, negative 7, because if it starts at 0, 0, then it would end at 5, negative 7. So it would move right 5 and down 7. So our x component is 5 and our y component is negative 7. Okay, so it shouldn't be 4, so I don't know why I wrote 4. It should be 5, negative 7. Boy, I'm all over my game today, aren't I? Okay. So we have our x and our y components. Okay? Now, then it says, well, what is the polar form of vector CD? Well, in polar form, we're not interested in x and y. We are interested in r, which is the length of the vector, and theta, which is the angle with the positive x-axis. Okay? So to get that, we're going to use two equations. The first equation is, based on the fact that you have a right triangle there, x squared plus y squared is equal to r squared. And our second equation would be for theta. Theta says that theta is the arctangent of y over x, because theta, tangent of theta is y over x. We want to solve that for theta. That would be the inverse tangent. Okay? So, to find r, we would do x squared plus y squared equals r squared. X is 5, y is negative 7. So that would be 25 plus 49. Which would be 74. Now again, that's not r, that is r squared, so we need to take the square root. This is another place where we will need our calculators. Now 74 is not a perfect square, and it is also not divisible by any perfect squares. So r is the square root of 74. As for theta, again, we've got that triangle where we have x is 5, y is negative 7, and we're being asked to find theta. Well, here in Chapter 8, we have discussed how that would be a tangent problem. Tangent would be opposite over adjacent. And then if we want theta, not tangent theta, then we would take the inverse tangent of each side. So theta would be the inverse tangent of negative 7 over 5. Now your calculator will always find the angle between the positive x-axis and the terminal side, or sorry, the vector, in terms of a half rotation. In this case, because we are rotating down from the x-axis in a clockwise fashion, our calculator is going to tell us that theta is negative 54.5 degrees. So if you are in the third or fourth quadrant, you should expect your theta value to be negative. If you are in the first or second quadrant, that would require counterclockwise rotation to get from the positive x-axis to your vector, which means you should get a positive angle. So our polar form of CD would be r, which is the square root of 74, at theta, negative 54.5 degrees. So there's our polar form. Okay, now this is a lot of new stuff, so I'm not expecting you to be great at this right away. Okay, so here in the next example, next two examples actually, they've already given us the component form of the vector. Okay, so if you wanted to, you could draw a quick picture. If the vector is located at negative 3, 4, if its component form is negative 3, 4, and it is in standard position, that would mean your vector AB is in the third quadrant. You would be going left 3 and up 4, just like you're graphing a point, which means you're looking at r being the magnitude, the distance from the origin to the end of the vector, and theta is the direction, which again is the angle between the positive x-axis and that vector, which means you should be expecting to get a vector that is an obtuse angle. So the magnitude, we would use Pythagorean theorem, just like we did on the last example. X squared plus y squared equals r squared. It is worth noting that magnitude is a distance, which means magnitude is always positive. So when we plug these numbers in, we have to be extremely careful. X squared would be negative 3 squared. You have to make sure you put that negative in parentheses before you square it in your calculator, or your calculator is going to lie to you about the value. We're looking at 9 plus 16, which would be 25. So r is the square root of 25, which we should all know is 5. Okay, as for the direction, when we're looking for the direction of angle theta, we would be doing the tangent of angle theta, even though that theta is not in the triangle. The tangent of angle theta, okay, what we have to do is we have to sort of consider this to be just the length of a triangle, okay, and we actually want to find the angle x, the angle in that triangle, okay. And the other thing we want to do is, since we're talking about a triangle, we don't want to use 3, or negative 3, we want to use positive 3. So the tangent of our angle x would be opposite over adjacent, 4 over 3. Which means that x is the inverse tangent of 4 over 3. We would feed that to our calculator and we would get 53.13 degrees. Now that is not theta, that is x. Looking at the picture, we should see that theta and x are a linear pair, which means that theta would be 180 minus x. So we do 180 minus 53.13, and that gives us our direction, which is an obtuse angle, 126.87 degrees. So our answer would be that the polar form of AD, the magnitude and direction, and again we've got that vector notation, would be r, which is 5, at theta, which is 126.87 degrees. Okay, if you think you've got it, pause the video and try the next one. You do need to pause the video though, because I'm not going to stop. Okay, we're going to keep going here. So if we're looking at the vector AB, where AB has component form, negative 4, negative 10, that would be in quadrant 3. We'd be looking at left 4, down 10 in quadrant 3. Okay, so when we look for angle theta, we want this angle here, which should be negative and obtuse. Okay? So again, we're going to end up finding angle x, and then r we still find exactly the same way. So the magnitude we always do the same way. We always do Pythagorean theorem. R squared is x squared plus y squared. And I realize I wrote that backwards what I did before. It doesn't matter. Okay, so that's not the x, that's the angle either. We're talking about this x is 4, right? So we have 4 and 10 for our component form. So we have r squared equals 4 squared plus 10 squared, which would be 16 plus 100. So r squared is 116. We would then take the square root. 116 is not a perfect square. However, it is divisible by 4. It is 4 times 29, which means we can reduce it to 2 root 29 for our magnitude. For our direction, we find the tangent of the angle in the triangle, which I am greatly regretting using x there, so I'm going to use a different letter. I'm going to use a, because we haven't used a for anything here. Okay, we need to find this angle right here, which is angle A. The tangent of A would be opposite over adjacent, 10 over 4, which means that that angle would be the inverse tangent of 10 over 4, and we would feed that to our calculator and get an angle of 68.20 degrees. Okay? Now, there are a couple of different ways that we can write this angle. Since we are in quadrant 3, our basic practice should be that since we're finding the angle between the positive x-axis and the vector, is that we should have a negative angle here. You also could think of this as being in the third quadrant, in which case you could find the angle between the positive x-axis and the vector, which would actually be more than 180 degrees. But I think we're going to go negative in this video here, okay? So first we would figure out what theta is. Well, theta and A add up to 180 degrees. So if A is 68.20, then theta can be found by subtracting 68.2 from that 180. So the angle itself is an obtuse angle of what? 111.8 degrees. But again, theta should be negative. So our actual angle would be negative 111.8 degrees. And I'm just going to quickly double check that calculation that I just did in my head. 180 minus 68.2. Yep, 111.8 degrees. But again, we are rotating in a clockwise direction, which means our angle should be negative. So our polar form for AB, our answer would be 2 root 29 at negative 111.8 degrees. Alternatively, we could have also come up with the angle here, which we could call angle phi. Okay, phi would be 180 plus A. So you could have also said 2 root 29 at 248.2 degrees would be an identical picture, okay? So either way, we would have a polar form, but generally speaking, we want our angle to be based on a location from the positive x-axis. The first two quadrants, 1 and 2, we would want that to be a positive angle. The third and fourth quadrants, we generally would want it to be a negative angle. Okay, so then the last part of this, we've got some stuff here that we need to talk about. In terms of direction rules, okay, in quadrants 1 and 2, theta is positive and acute in angle 1. In quadrant 2, theta is positive and obtuse. In quadrant 4, theta is negative and acute. Again, this has to do with clockwise rotation up from the positive x-axis, or counterclockwise up, or clockwise rotation down. Okay? Okay. So, and then in quadrant 4, our theta is still negative because we're rotating in a clockwise fashion, but it would be an obtuse angle. Okay? Now later on in pre-calc, these rules are going to change. In fact, they're going to change even more than that, because in pre-calc we won't actually be using degree measures anymore. We'll be using radians. In most of your AP courses, we will not measure angles in degrees. All right, so next up here we have convert each of the following polar form to component form. So to go from component to polar, we just did a couple of those. So to go from component to polar, which is r at theta, we had two equations. We used r squared is x squared plus y squared, and we used that theta is the arctangent of y over x. And that theta actually requires more thought than that, depending on what quadrant we're in. Now to go from polar, again that's r at theta, to component is actually significantly easier because it is a straight substitution. X is always r times the cosine of theta, and y is always r times the sine of theta. And there'll be a lot more explanation of that in your trigonometry course down the road. So with these problems here, we're just using a calculator. We are given an r and a theta. All we need to do is figure out our x by doing 13.5 times the cosine of 68 degrees. And we're going to round that to the nearest hundredth. So we get 5.057. So we're going to call that about 5.06. And we're going to do y equals 13.5 times the sine of our theta, 68 degrees. Same deal, we're going to just round that to the nearest hundredth, 12.516. So y is about 12.52. Then we write it in vector forms. We need these triangular brackets to indicate that it is a vector. 5.06, 12.52. Okay, on the next one, again, we have an r and we have a theta. So all that we have to do, get my theta to actually look like a theta, that would be helpful, is figure out our x, which is 22.5 times the cosine of negative 74 degrees, which would give us x is approximately 6.201. Now we should think that that makes sense logically. Negative 74 degrees is in quadrant 4. In quadrant 4, x is still positive. So we're going to be using 6.20 to be our x component. Our y component would be 22.5 times the sine of negative 74 degrees. Again, that's in the fourth quadrant, so when we plug this into our calculator, it should not surprise us to see a negative number come out. So that gives us y is approximately negative 21.63. Again, we then write our answer in component notation, triangular brackets, x, comma, y. Okay, last one, r at theta. Again, if you think you got it, pause the video before you watch the example here. So 19.3 times the cosine of 138 degrees. Now that is in quadrant 2, so when we feed that to our calculator, we should expect exactly what we get, which is a negative x value, because in quadrant 2, x is negative. So we're looking at an x component of negative 14.34. And for y, 19.3 times the sine of 138 degrees. Again, in quadrant 2, all of our y values are positive, so we should not be surprised that we get a positive y value of 12.91, rounded to the nearest hundredth. So again, our answer is negative 14.34, comma, 12.91 in those triangular vector brackets. Okay, the last piece of this unit is that vectors in component form can be added and subtracted like other numbers. Basically, we have our AB and our CD. Okay, what we do is we add the x components together. Okay, we add our x components together, which is A and C. Okay, so if we have A, B as one of our vectors, and CD is our other vector, not used yet, pink, there we go. Then what we do is we add the x vectors together, A plus C, and we add the y vectors together, B plus D. The same would go for subtraction. And then the last thing would be that if we multiply a vector by a scalar, which is what we call a non-vector number, then we simply multiply both components A and B by that k value. So we end up with k times A, k times B. Okay? So on the surface, that sounds incredibly easy, and for the most part, it is. Okay? On number 1, we're asked to find vector A plus vector B. So vector A is negative 2, 5. Vector B is 8, negative 3. So we are going to add negative 2 and 8 together and add 5 and negative 3 together. So our answer would be 6, 2. Okay? Now if we have a vector, or if we have a scalar multiplication first and then say a subtraction, like 5 times vector D minus 2 times vector C, we would write that as 5 times vector D, which is 0, negative 7, minus 2, should use that triangular bracket, times vector C, which is negative 5, negative 6. So first, we are going to multiply both of the numbers in the first vector by 5 and both of the numbers in the second vector by negative 2. That would give us 0, negative 35, plus 10, 12. Now you could also write this as minus negative 10, negative 12. Then we apply what we did before. We add the x components, 0 plus 10, and we add the y components, 35 plus 12. That would give us the vector 10, negative 23 as our answer. Okay, this can get as complicated as we want it to get. I do kind of regret my spacing here. 2 times vector D would be 2 times 0, negative 7, minus vector A is negative 2, 5, and then plus 2 times vector B, which is 8, negative 3. So again, we're going to start by distributing. We're going to send the 2 through the first one and the 2 through the last one. That's going to give us 0, negative 14, minus negative 2, 5, plus 16, negative 6. Then we are going to combine the first two. 0 minus negative 2, negative 14 minus 5, which would be 2, negative 19, plus 16, negative 6. And then we're going to combine those two. 2 plus 16, negative 19 plus negative 6 is 18, negative 25. Okay, lastly, number 4. I had to adjust a little bit there. We've got vector C, which is negative 5, negative 6, minus 3 times vector B, which is 8, negative 3, plus 2 times vector A, which is negative 2, 5. So again, we start off by multiplying negative 3 and positive 2 into these vectors. So we would have negative 5, negative 6, plus negative 24, 9, plus negative 4, 10. We would combine the first two vectors, so negative 5 plus negative 24, comma, negative 6 plus 9. Simplify that would be negative 29, 3, plus negative 4, 10. And then we would combine those. Negative 29 plus negative 4, 3 plus 10. To give us our final answer of negative 33, 13. So again, it's just like order of operations. We have to multiply first, so we would always do scalar multiplication before we would add or subtract. And we add or subtract at the same time, moving from left to right. So don't try to do too much at once. All right, that's all we do with vectors in honor geometry. Thank you very much for your time and attention.